We left off last time with a vodcast that talked about the properties that describe a gas. And this is on another page of the notes, so don't worry about writing anything right here. A gas can be described by its volume, pressure, temperature, and the amount of gas measured in moles. We're going to focus in this short vodcast on that property called pressure. Now let's take a look at the definition of pressure. That stands for force per unit area. Well, that doesn't mean much to me, but perhaps what I can do is show you a picture. Now, if your goal would be to walk across that snowbank without falling through the crust of the snow, would you pick A, the skanky horseshoe on the left, or would you pick B, the snowshoes? So I'm hoping that you realize that the snowshoes are going to distribute your mass over a wider area, therefore reducing the pressure. Let's take a look at that again. If area is on a denominator, and if you take area from a small skanky horseshoe area to a large Canadian normal walking shoe area, the bigger the number is on a denominator, then the smaller the number is overall. So you still have the same mass, assuming this skanky hoe person is walking on the crust of snow. You have the same mass pushing down, but it's distributed over a larger area and there is less pressure, hence you're able to walk on the snow without breaking through the crust. With that lurid detail then, hopefully you understand that the force is the force of gravity that is being applied to the human's mass, pulling downwards towards a bigger mass, the center of the earth. And if you have a large area, it exerts a lower pressure overall. Well, gases exert a pressure on us. Take a look at some of the components of the sea of air that's above us right now. So there's this giant sea of air that goes up for miles and miles from the earth. But what is actually in air? It's about 78% nitrogen. A lot of times I just say 80%, 21% oxygen, and 1% other gases like smog or inert gases or, I don't know, carbon dioxide. So even though we're breathing nitrogen, because there's 21% oxygen, that's enough for us warm-blooded oxygen-breathing creatures to survive. And what you have to visualize is pretend that you are the person down here on looks like the Canadian-United States border. And if you could actually measure the mass of a one-by-one column of air that's being pushed down on your pointy little head, that would be a huge amount, 10,000 kilograms of oxygen, nitrogen, and other miscellaneous gases being applied on you over that square meter. Well, we call that definition to be 1 atmosphere of pressure. That would be at sea level on a normal day, not high up in the Andes or the Himalayas, but also not down in Death Valley. You're at sea level, which is first floor Redwood High School, by the way, and that's the amount of pressure that we would call 1 atmosphere of pressure. You don't feel that pressure as being uncomfortable because you as a creature have evolved on the surface of the planet, and that's normal for you. So you can also express this in a more antiquated way, but you'll still see it on bike tires and automobile tires because the United States in its wisdom did not go metric in the 60s when they said they would. And we call PSI pounds per square inch. And there are 14.7 pounds on every square inch of the surface of the earth and you on your body if you're at sea level on a normal day, no hurricanes passing through. We don't use PSI in chemistry, so look at it, forget about it. The first 4 miles of the atmosphere, or first 4 miles up, have about half the atmosphere. If you go another 10 miles, 90% of the atmosphere is taken into account. And within about 20 miles, almost all of our atmosphere is accounted for. You don't need to remember these numbers. They're just fascinating factoids. But hopefully what you've done by now is the barometer worksheet, which describes how it is that we measure pressure. Now, this is for the pressure of the atmosphere, not for a contained gas. And let's take a close look at that. Air pressure would be pushing down on this open puddle of mercury. There's a tube that points up, and there's a little bit of a space at the end with a vacuum. And these numbers aren't correct. It's 29.95 inches and I would call that 760 millimeters instead of 76 centimeters. If it's a normal day at sea level, the column of mercury that would rise up in the column from the air pressure pushing down would be those distances. And that's standard pressure. So this 760 millimeters of pressure was recognized hundreds of years ago, no matter where it was being measured, as long as you were not up in the mountains somewhere. So let's take a look at it again. At the tip of the mercury manometer or barometer are some mercury vapors, not too critical, and the downward push of the air pressure will push the liquid mercury up into the column. So when the weatherman says, hey, we're having a high pressure system going through, barometer is rising, they're talking about the level of the mercury rising in the tube. Or if we have a severe storm coming through, those are associated with low atmospheric pressure, and he'll say the barometer is falling, or she will. Okay, so what happens when you go up to high altitudes? So the atmospheric pressure as you're trundling up, Mount Everest with your Sherpa carrying all the heavy stuff, is that the higher up you go this 5-mile high mountain, then the less atmosphere you have pushing down on you. So that makes sense. And if you've ever traveled up to, say, Lake Tahoe or anywhere in the Sierra, as you put your potato chip bag in the back of the car, when you get up to like Donner Lake or Lake Tahoe, you look at the bag, it's all poofed open. That's because the pressure on the outside of the bag is decreased, so the pressure of the inside of the gas that's trapped with the chips is pushing out and away. And that's what pressure is for gases. If it's a trapped gas inside a container, when the molecules strike the inner edges of the container, that's what defines their pressure. So going up high, up into the atmosphere, you'll have less pressure pushing down on you. That's why if you do climb Mount Everest, you generally are bringing bottled oxygen. And there's a few climbers that don't do it with the oxygen, but they're not normal humans. So we're going to define what standard normal pressure is. If you're at sea level on a normal day, standard pressure is the pressure required to support a column of mercury in the barometer that's 760 millimeters high. Now this is one of many measurements of pressure, and our focus now will be to recognize some common forms of pressure measurement and how to convert from one into the other. Well, we can call the measurement of pressure 760 millimeters, and that's how we rate like barometers, for example. However, people said, it's kind of weird that those millimeters, a unit of length, are being used to talk about a force per unit area. So let's just call that 1 atmosphere. When you do the math with that guy, it's super easy. If you do something cool in science, they name a unit after you. So Torricelli was one of many early Italian gas researchers. And so they said, instead of calling it a millimeter, why don't we just call it a torr, which is short for Torricelli. So the number's the same, but the unit changes. The metric system, though, requires that we use pascals, and kPa stands for kilopascals. So that would be 1,000 pascals, and that would be if you took a Newton's worth of force. Let's describe that. Take a brick that weighs a little over 2 pounds, and if you spread the mass of that brick over a square meter area, and it's pushing down due to the attraction of gravity from the earth, that's what we call a pascal. And we round this off to 101.3. Okay, there's another way that you can measure pressure, and I think the units fell off of there, but that should have been a 1.013 bar or 1013 millibar. Don't use that too much, so don't worry about it. And as we've indicated, those are all measurements of standard pressure. You can also measure in inches, which is 29.95 inches. And the reason I put that there is because in a lab that we either have done or will do, Charles Law Lab, we measured the barometric pressure in inches because that's sort of the United States standard, but we're going to need to turn it into millimeters, and I will show you how to do that. Okay, so those are the units of standard pressure for measuring either the pressure of a gas that's trapped inside a container or the pressure of the atmosphere all around us. But there's a specific device called a manometer, which is used to measure gas pressure. And gases confined in a container push on the inner edge of the inner walls of that container. and you can measure that pressure using a manometer. Now there's a manometer worksheet that you will be completing after this vodcast, so pay careful attention to how it is that we can calculate the pressure of a trapped gas. So all of this stuff that you're now going to see in the notes is kind of gibberish. I'm going to actually go to the picture for us to explain how manometers work. It's not really gibberish, but after you see the picture, you'll understand it better. It requires doing some very simple math. We're going to be either adding or subtracting the difference between two values. So let's take a look at it. Now these are very simple manometers, and they are what we call a closed end, well, not really a closed end, an open end manometer, because they're open to the pressure of the atmosphere pushing down. And this end is sealed, and they're filled with something like mercury. And where the height of this mercury is going to tell us whether the pressure of a gas trapped inside is greater or less than the pressure outside. This picture doesn't show a real manometer though, but let's go ahead and identify that we might have atmospheric pressure of 760 millimeters outside pushing down on the open end of the manometer. And if you push down here with increasing pressure, you'll rise or raise the column of mercury over here on the left-hand side. Sometimes they flip them over, so the open one's on the left and the closed one's on the right. It doesn't matter, it's the same process. Much better picture here. Okay, so if you look at this manometer, an open-end manometer, now you see what they really look like. A gas is trapped here. When you open the valve, gas pressure comes up, out, and pushes down on the column of mercury on this side. There's a battle going on though, because the pressure of the atmosphere is pushing down here as well. And so basically, don't worry about all that open and closed stuff that you see there. Just ask yourself, based upon the difference between the levels of mercury, and that's what this distance here is measuring, you find the distance between this line and that line, and it will be a certain value that we'll use in a simple math calculation. But right now, qualitatively, study the picture for a second and then decide who is stronger now in this battle, the pressure of the interior gas trapped in the container or the pressure of the atmosphere pushing down on the open arm. If you said that the interior gas pressure of the trapped gas is stronger, you're correct, because the level of the mercury here is lower than it is over here. If you can accept that, then what you're able to do is to be able to calculate the difference between the two arms of mercury, and you will either add or subtract them to the outside pressure. So let's think about that. Let me see if I can get to the correct slide, because this isn't helping me too much. When you actually measure, I haven't given you any numbers so you couldn't do it. Let's say, for example, this was some amount, this height of this column of the mercury here, subtracts the height of the column of the mercury here, and the answer you get is 50. That's the difference between the two columns of mercury. You recognize, because of the picture, that the outside gas is pushing, or excuse me, the inside trapped gas, the trapped gas in the manometer, is pushing stronger than the outside pressure. So what that means is that the gas inside must be greater than the pressure outside. How much greater? 50 millimeters of mercury pressure greater. So you take the outside pressure given and you add the difference between the two arms of mercury heights, and now you know the pressure inside for the trapped gas is 810 millimeters of mercury. That's how you do it if the pressure inside is greater. Now look at this picture, and hopefully you can recognize that the pressure inside must be less, because the outside pressure, still 760 in this context, is pushing down with more force, so the level of mercury on the left-hand side is lower than the level of mercury on the right-hand side. We still find the difference between this height, so you have to take the total height here, and this height. Find the difference between those two, and this time, since the gas pressure inside is weaker than outside, That difference of 20 millimeters of mercury will not be added, but you guessed it, subtracted from 760. So the pressure of the trap gas is only 740 millimeters of mercury. It's really just that simple, but you have to look very closely at whether this is an open-end manometer or not, and also judge first which is stronger, the pressure of the inside gas or the pressure of the atmosphere. When you do the worksheet on measuring pressure, you will see a closed-end manometer. That's very simple, and it explains in the worksheet, so it won't mean much right now. To get the pressure of a trap gas and a closed-end manometer is just simply the difference in the heights of the two columns of mercury. We'll stop there until next time.